This video is part of an online course of multivariable calculus, and I'm going to talk about the fundamental theorem for line integrals. So let's take f as a vector field that is defined on a curve C with parametrization r of t, where t is between t1 and t2. That is basically the parametrization of C. Okay, then we say the line integral of f dr over the curve C is the way that we evaluate this integral is to parameterize the curve C, which we have, and then we're going to plug in our parameterization into the vector field, and then the r that we have in here would be derivative of the parameterization, so r prime of t dt, where t is between t1 and t2. Okay, so that's how we write the line integral over a vector field. We talked about this on previous videos. Now let me give you a definition. We say that the vector field f is conservative if the gradient of a function is equal to, or vector field, basically, or vector field is equal to gradient of a function. Let me actually write it this way. The vector field f is gradient of f for some function f. Okay, so this function f that we have in here is called potential function. Potential function. So we say that a vector field, it's a vector field is conservative if the vector field is actually gradient of some function f. Okay, then we have the fundamental theorem for line integrals. Fundamental theorem for line integrals. For line integrals. Okay, it is what? The fundamental theorem for line integrals says that if the vector field f is conservative, meaning that it's gradient of some function, and if the curve C is a parameterized curve, from P1 to P2, then the integral of f dr over the curve C is equal to, so what do we have in here? We have a conservative vector field f. So f is conservative, and then we have a curve C that is from P1, which is basically r of t1, and then it goes to the point P2. So P1 is the first point, P2 is the second point. Okay, is the end point in here. Then the line integral for the vector field f that is conservative is actually the potential function at the end point minus the potential function at the first point. Okay, so if I want to go back to the fundamental theorem of calculus for one variable function, it was like this. If you remember, the integral from a to b, an interval of a to b of f prime of x dx, it was f of b, the end point of the interval, minus f of a, when we have the interval from a to b. Okay, that was the fundamental theorem of calculus. But fundamental theorem for line integrals, okay, for line integrals is this one, that the integral of a gradient of a function f dr over the curve c, it is f, the potential function at the endpoint, minus potential function at the first point. If you just want to compare the fundamental theorem of calculus and fundamental theorem for line integral, you see that we have derivative of the function in here, we have gradient of a function in here, and then the function at the end point minus the function at the beginning point. The same is here. Let me give you one example, and then I'm gonna go over the proof for that. Okay, so the example is this. Let me actually keep in here example. Let the vector field f to be xi plus yj. Okay, find the integral of f dot dr over the curve c, where the curve c is the interval from 0 to 1. Let me graph it. X-axis, y-axis, and then c is basically here from 0 to 1. Okay, so you see, the good thing about the fundamental theorem of calculus is that we are saying that if the vector field is conservative, meaning that the vector field is gradient of a function, you don't need to calculate the line integral, parameterizing c, and then plug in your parameterization into f, and then derivative of the parameterization, that dt. It's a long way to solve it, but instead you can just find the potential function, plug in the endpoints minus the first point. Okay, so I can guess that if the function f is 1/2 x squared plus 1/2 y squared, then gradient of f, which is what? Gradient of a function f would be fx, partial derivative with respect to x, and partial derivative with respect to y. Partial derivative of this function with respect to x is x, and with respect to y, partial derivative would be just y. As you see, this is your vector field, your given vector field, f. Perfect. So I found the potential function. So this vector field, the given vector field, is conservative. So I can use the fundamental theorem of calculus in here, the fundamental theorem for the line integrals. So by the fundamental theorem of line integrals, the integral of f dr over the curve c is actually the potential function at the end point, which is what point? The point 1 and 0, minus the potential function at the first point, which is 0, 0. So what is f at 1, 0? Plug in 1 for x, 0 for y. So it is 1/2. And then plug in 0, 0 in here, we get 0. So the answer for this line integral is 1/2. Okay. If I want to use the previous way to calculate this line integral, I needed to do what? I needed to parameterization of c. It's what? C is here, so I can say that I'm gonna set x to be 0 and then y to be equal to t, where t is between 0 and 1. Okay, so the line integral of f dr over c is equal to what? Is equal to f is x and y, and then I have dr over the curve c, where the curve c is actually 0 and t. So this is basically r of t. Now r prime of t is 0 and 1. So this integral is from 0 to 1, and then x is plugging the parameterization into f. So x is 0, and then y is equal to t. And then I have r prime of t, which is 0 and 1, and then dt. Okay, so we have a dot product between these two vectors. So if I want to find the dot product, it would be the integral from 0 to 1, and then the dot product is t dt. So this is t squared over 2 from 0 to 1, 1/2. As you see, we get the same answer using the fundamental theorem of line integrals and using the answer for the line integral. Okay, but this one was so much easier if I can find a potential function. Very good. Now let me go back to the fundamental theorem of line integrals, and I'm gonna give you the proof. So let me have some space in here, and I'm gonna give you the proof for that. So for the proof, I can say the integral of c of the gradient f dr is equal to what? It's equal to the gradient of a function would be fx, fy, and then dr has the notation for dx and then dy over the curve c. I have a dot product between these two vectors, so it would be fx dx plus fy di. Very good. Now let me parameterize the curve c. I'm gonna let x to be x of t, and I'm gonna let y to be a function y of t, and then in that case dx would be x prime of t dt, and then dy would be y prime of t dt. Okay, now let me plug in the parameterization into here. So what do I get? I get the parameterization t is between t1 and t2. So I have from t1 to t2. So I get what? Fx is what? It would be the partial derivative of f with respect to x, and then dx is x prime of t, which is dx dt, plus I have fy, which is what? Partial derivative of f with respect to y, and then dy dt, and then dt. Very good. From t1 to t2. Now, what do we have in here? Let me have more space. Okay. So as you see, this definition that I have in here is basically the chain rule. It's what? From t1 to t2, and then it is ddt of f of x of t and then y of t, right? So basically I have chain rule in here. So I have what? I have antiderivative of this function. Okay, so it would be the function itself and then y of t. Okay, and it's from t1 to t2. So what? F of x of t2 and then y of t2. Let me write this. F of x of t2 and y of t2 minus f of x of t1 and then y of t1. Okay, so the parameterization at the time t2, it's the point p2 minus the parameterization at the time t1 is the point p1. So the line integral that we have in here, let me show it to you, the whole proof. So this line integral of the conservative vector field is f of p2 minus f of p1. Very good. So that's end of the proof. And now I'm going to talk about consequences of the fundamental. Now I'm going to talk about consequences of fundamental theorem for line integrals. The first one is that if f is conservative, then the integral of f dr over the curve C depends only on the point P1 and P2 and not on the curve C. That is what? That is, it is, let me say, i.e., this line integral is path independent. So what I'm saying is that if we have 2 points P1 and P2, if we go along this curve C1 and go from P1 and P2, and then if we go along this curve C2 and go from P1 and P2, then the integral of f dr over C1 is equal to the integral of f dr over C2, because the curve is not important, just the beginning and the end point is important. And the question is why? It's just because of that. Because f is conservative, the vector field f is conservative, that's why we have the integral of the gradient of some function dr over C1, and this is actually the integral of f dr over C2 because the integral of the gradient is just the potential function from P2 and then f of P1, the difference between these two. So as you see, these two integrals are the same. It's just because the beginning and the end points are the same, and then we just need to plug in the end point and the beginning point into the potential function. Okay, so that's why if the vector field is conservative, the line integral of the vector field f is only depending on the beginning and the end point, and the line integral is path independent. Okay, for the consequence 2, I need to give you just one small definition, and the definition is this: a curve C from P1 to P2 is closed if the beginning and end points are the same. So for example, if we have something like that, this curve starting at here and it goes right there, and then the beginning and end points is the same, this curve is closed. Okay, then we say what? We say that if f is conservative and let me provide some space. And the curve C is closed. Then the integral of the vector field over the closed curve C is equal to 0. Why? Why? It's just because the integral of f dr over C is potential function at the endpoints minus potential function at the beginning point, and since these two are the same, so I get 0. Therefore, we cannot extract energy for free from a conservative vector field such as gravitational vector field, because if f is conservative, then the integral of that, or basically the work done for a conservative vector field over a closed curve, is 0. Let me give you a remark. And the remark is that, in fact, these two properties, which one? The one that when f is conservative, the integral of f dr over the curve C is path independent, and the integral of f dr over a closed curve C is 0. So these two properties are equivalent. Why? It's just because, so we start at the point P1 and then we go to the point P2. We go along this curve C1, and then to make it close, we say if we actually go along the curve C2, let's say the curve C, which is equal to C1 minus C2, is closed. And so the integral over C is equal to 0, right? And then we say that, actually let me write it complete. The integral of f dr over C is closed, is 0, right? And so C is defined as C1 minus C2, because on the opposite direction. So it is what? It is the integral of f dr over C1 minus the integral of f dr over C2. This is equal to 0, which means what? Which means that f dr over C1 is equal to f dr over C2. As you see, this integral is path independent if the integral over the closed curve C is equal to 0, and then if the integral over the closed curve C is equal to 0, it's path independent. That's why these two properties that we discussed, these two, number 1 and number 2, are equivalent to each other. So we have a very good theorem in here. The theorem is this: f is conservative if and only if the integral of f dr over the curve C is path independent. Which means that it depends only on endpoints. And we can say that f is conservative if and only if the integral of f dr over the curve C is equal to 0 for all closed curve C. Closed curves C. Okay, so it's a good theorem that says that if we have any of these two properties, it means that the vector field F is conservative. And then when the vector field F is conservative, then the line integral is path independent, and the integral over all closed curve C is 0. Now let me give you one example so that you see these two properties. Example, let the vector field F to be negative 1i plus 8y j. Okay, is it conservative or not? Let's say, can I find a potential function f such that gradient of that function is equal to f? Let the function f to be equal to negative x plus 4y squared. And then if you find gradient of f, which is fx and then fy, as you see, partial derivative with respect to x is negative 1, and then partial derivative with respect to y is 8y. So should we always guess the potential function, or there is a procedure to do it? Actually, I'm going to explain that in the next video, but for now, let's keep this one. Now let's have the curve C, x-axis, y-axis, and the curve C is just the line from negative 1 and it goes to 1 and 0. So this is negative 1 and 0. I'm gonna call this C1. So as you see, the integral of f that dr over C1 is equal to what? It's equal to the potential function at the endpoint minus potential function at the starting point. Okay, plug in 1 and 0 in here, so I get a negative 1, minus plug in negative 1 and 0 in here, I get a 1, it's negative 2. Okay, now this is using the fundamental theorem of line integrals. If I want to calculate this line integral using parameterization, I'm gonna find the parameterization in here. So it would be the line segment from P1 to P2. P2 is 1 and 0, P1 is negative 1 and 0. Okay, so I'm gonna say that R of t is equal to the first point plus t, the difference between the second point minus the first point. So 1 minus negative 1, it would be 2, and then 0 minus 0 is equal to 0. So I get a negative 1 plus 2t, and also 0, where t is between 0 and 1. That's the parameterization that I chose. So r prime of t would be equal to 2 and 0, derivative of r of t. Now let's plug in everything into the line integral. So what do I have? It's from 0 to 1. The vector field is negative 1 and 8y. So 8. Instead of y, I need to plug in the parameterization in here, which would be 0. And then r prime, 2 and 0, and then dt. Okay, so it would be what? It would be negative 2. So it would be 0, 1, negative 2. And then dt, so the answer negative 2t from 0 to 1, plug in, I get a negative 2. Okay, now let's check. If I go from the point P1 to the point P2 along this part of a circle. That was not a good circle. Let me change it to that. Not bad. C2. It's part of a circle of radius 1. So let's see what's gonna happen. It's the upper half of the unit circle. I'm gonna parameterize it as cosine t and then y of t to be sine t, where t is between 0 and pi. Okay, and so it's from here to here, so t should be from pi to 0, but it doesn't make sense. That's why it's kind of like backward. It's clockwise rather than counterclockwise. Okay, so x prime of t is negative sine t, and y prime of t is equal to cosine t. Now let's see. I have the integral of f dot dr over c2. It's equal to what? It's equal to from pi to 0. It's just because I'm moving from here to here, okay? Or actually, you can write this instead of that. You can write this in the usual way from 0 to pi, but with the negative sign, just to mentioning that I'm starting it here to here, okay? And then the vector field f at or parameterization, which would be -1 and 8y, 8 sine t, and then r prime of t, which would be negative sine t and cosine t, and then dt. Okay, so it's negative the integral from 0 to pi. Let's find the dot product, which would be sine t plus 8 sine t cosine t dt. So for the integral of sine t, let me have the negative sign in here, and then integral of sine, it would be negative cosine t from 0 to pi, and then I have a negative sign. The integral of here, I'm gonna use u sub. I'm gonna take u as sine, and then du would be cosine t dt. Okay, so I get what? Negative 8 sine square of t over 2 from 0 to pi. So what do I get? Cosine of pi is -1 times another negative positive, so I get a -1 in here, minus, I have negative would be positive, cosine of 0 is 1. Okay, and then on here I have sine of pi, which is 0, sine of 0 is 0, so this one would be all together would be 0. So the answer, I got -2. Now let's see what we have. Okay, we go from -1, 0 to this point. Let me call this one P1. I'm gonna call this one P2. I go from P1 to P2 along C1, I get -2. Along C2, I get a -2, as you see. And if I consider C as a closed curve, C as the closed curve, to make it close, I'm gonna go C1 and then negative C2. So C1 minus C2. So the integral over C would be the integral over C1 minus the integral over C2. So the integral over C1 is -2 minus the integral over C2, which is -2. So I get a 0 in here because the integral over the closed curve C is 0, and everything that I have in here is just because my vector field is conservative.